Hey, I'm Chris Biscardi, and today we're going to talk about visualizing 2D Perlin noise like you see before you. So if I quickly hit grayscale here, this image is constructed using a grid of X and Y positions that are put into a two-dimensional Perlin noise algorithm, which spits out a number for us. We then convert that number, which is from -1 to 1, into the range 0 to 255 or something like that we can use to define a color for that particular position on the screen. Now, this is a 6-octave variant of Perlin noise, so there's quite a bit of variation in here, and we've chosen to go grayscale for the moment. But also note that we can go into color whenever we want to. And you can see that I have a little bit of control over what colors we use, even though the grayscale is still the exact same. And every time we click on this, we can get a different seed, which produces a different set of Perlin noise. Now, to change these values, I've also included an eGUI UI, which includes the lightness, chroma, hue center, hue range, and whether we're grayscale or not. So when I boot this up by default, we end up with a Perlin seed value of 0, which gives us this nice, beautiful gradient. We're using the LCH color space, which is a polar version of Lab, which gives us the same perceptual lightness across this image. Now, I do think that I have a couple of translation issues in the color here, which is why you can see the blue being a little bit more blown out, but that's not terribly important. We can use the eGUI UI to lighten or darken our image, saturate or desaturate our image using the chroma value, or change the center of our hue. Now, LCH is rotational, so it is a hue value from -180 to 180 degrees on a color wheel. So as I move this, we're basically moving 0 to 145, which changes which colors appear where. I can also change the hue range if I want to say get rid of that red and make this a nice blue, yellow, green image. Maybe saturate it a little bit more, get a little bit more green in there. But this is basically what we're going to build today. And of course, we can always go back to the grayscale to see sort of what the pure Perlin noise values are actually outputting. So in this case, we again use the noise step of 500, which means we're going to use from 0 to 1 about 500 steps of Perlin noise. So the input to our Perlin noise is going to be something like 002, 004, 006, and so on. Of course, we're using Nannou, so we have to set up Nannou in our main function. This sets up our model, which is only run once, and then the update function is run on every update. In this case, we have a number of settings in a struct. You can see the lightness and the chroma values that we had on the slider in the eGUI UI, as well as the grayscale checkbox and the hue center and the hue range. I've chosen to represent this as a hue center and a hue range so that we can move which colors at which position, which is the center, and then also either restrict the range to something that is, say, just greens or the full color spectrum. And these are all float 64s, which means that we have a massive space to work with. We actually don't use the entire float 64 space. LCH is often capped between, so let's say, -180 and 180 total, depending on which value you're working with. So we don't actually use much of this F64 space. That's just to make it easier to work with the output of the noise functions and the inputs of the other color functions. Our model here is where all of our state lives. We set the settings in here on a settings field. We set up our eGUI in here, and we set a window ID. You can see that I had two windows, one for the eGUI like debug UI and one for the actual image itself. So this represents the image window. This should redraw as just a convenience function for some eGUI changes. In this particular sketch, we do all of the image generation in our model function. So when the update runs, if nothing has changed, we don't need to do any more processing. So to prevent that extra load on our CPU and GPU, I've just implemented this optimization. We use basic multi like we did for the single dimensional Perlin noise in our last video. So I'll refer you to that video if you didn't quite get the description here. And then we have a dynamic image, which is what we're filling the noise values into, and then the size of the actual image that we need to create. We'll talk a little bit more about dynamic image in a moment. I'm just going to collapse a couple of these functions on the model struct for a moment, and we'll talk about the model function first. To start off with, we start with creating our image window, which is where we're going to display the Perlin noise, the window that we're going to render our image into. Create a new window, make the size nice. I choose this size because it works really good on things like Twitter, but you can see that I also just made it full screen to talk at the beginning of the video. So you can change that as much as you want, and this will actually update. You'll see right below, we also create another window for the eGUI, We don't actually have to create two windows here. I just chose to because I kind of like having my controls separate from the thing that I'm looking at and not overlapped on top. For each window, we have a different view function. One of them controls the view or the rendering of the settings debug menu, and the other one controls the actual rendering of the Perlin noise. In this case, I've also used the key press for save and the mouse pressed for creating a new seed that we talked about in the last video. And this raw event just kind of is some wiring to hook up eGUI to the other window. Then we have some glue code here to, reconnect eGUI to the window again. And we create model new with a couple of values that we'll talk about in a second. Basically, this is, do we want to set the noise seed? We have to pass the eGUI, which we've attached from the window in. And then we have to specify which window is the image window, because in our update function, we detect if this window has changed, and we have to have that value for us to know if it changed. So our update function is exactly what I just said. This is the update for everything. So we don't get to split the update into the update for the eGUI stuff and the update for the actual rendering. So in this case, we get the size of the window from the image window. So this is the one that we're rendering the Perlin noise into, and we get rect at the end. We can use rect to check against the model size that we've stored when we created the model in the first place. If the width and the height have changed, or if the should redraw flag is set, then we can redraw the image. We just unset should redraw. We update the size on the model and we redraw the image. Now, in this case, we are drawing this image by constructing the entire set of Perlin noise that we want to use and putting that into a texture and then rendering the texture later. But we'll get into that when we get into the actual model code. Below all of this model rendering code, we get the eGUI settings. So our model.settings is where we keep all of our color values, our ranges, and things like that. So we grab that from the model as a mutable reference. And we also grab the eGUI from the model as a mutable reference. We can set the time and begin the eGUI frame. In this case, we create a new eGUI window, which is the little thing inside of our actual window, and we name it settings. eGUI gives us a context and a UI variable, so we just kind of accept those. We're going to use the UI to set up all of our debug UI. At the top of this function, we have a changed variable. This changed variable is something that we will use to detect if there have been any changes to any of the settings. If there are any changes to any of the settings, at the bottom here, we just check if clicked or changed. So if we click this update or any of the values have changed, then we set this redraw flag, and then in the next update, we'll actually get a new image. The eGUI code is pretty, regular. They all follow the same pattern. We construct some eGUI component. In this case, we very much have a bunch of sliders. So we pass in a mutable reference to the field that we want the eGUI to set. We pass in the range that we want that slider to be capable of setting. So in the case of lightness in LCH goes from 0 to 100. Then we set a label in the UI and we add the component. Now, when we add the component, we also check if it changed. And because this is all immediate mode, this may feel a little weird if you're not used to immediate mode rendering frameworks, if you haven't worked on the web very much. But basically, this changed function returns a Boolean. This changed variable is something that we set on 191. And this is or equals, which is a little confusing. I think I'm going to take that out of this code example because it's not an operator that you see very often. But basically, if .changed is ever true, then this change will become true. It's basically like saying false or true, or false or false. If it's false on both sides, then it's false. If it's true on one of the sides, then it's true. And we do the same thing for the other sliders. We do a chroma slider. Chroma values can go from 0 to, I think they are technically infinite, but this is basically saturation, and saturation is slightly different for each color in this color space. So we go from something like 0 to 120 or 0 to 180 technically. So I've just maxed it out at 180, and that's that. You could choose a different number here if you wanted to. We do the same change to Trek to detect if it changed. And then we do the same thing for the hue center. The hue center now is a rotating color wheel. So it's 360 degrees centered on the number 0. So what we get for our slider is negative 180 degrees to 180 degrees. And this will rotate. So our hue range down here is anything from 0 to 180. When we actually go to construct this color, we will take the hue center. So if this is at 0 and then the range is 180, we'll do 0 minus 180 and 0 plus 180. And that will be the range that we map our Perlin noise into to pick a hue. So by combining these two, we can say set the hue center to say 180 and set the hue range to 10. And then we'll have something between 170 and 190 for our hue range. We do the same thing as the sliders for the checkbox. This is just whether or not it's grayscale. This has a little bit more of an impact because we change the way that we generate the color, which we'll go into when we get into the model code. And then we have this update button. I was kind of using this when I was developing. It's a button. We click it. It sets the should redraw flag. And in the next update, we check this flag and see if we should re-update. So now we're left with the view and the model code. So let's go back, and this is really the juicy part of sort of the Perlin noise generation. Our model here is this struct. So it's got some settings. It's got a reference to eGUI in the window and whether it should redraw or not. But it's also got noise, image, and size. And noise and image are the two really big things that we care about here the most. So this new function optionally takes in some noise. So if we seed the noise later, which we can do whenever we click, then this will be set. And then we've got eGUI and image window, self-explanatory there. The really interesting part is this dynamic image. So we create a new RGB8 dynamic image, and we're going to take this image and we're going to fill it up pixel by pixel with the noise values that we get when we put in an X and a Y value. So all we're doing here is instantiating any dynamic image. We could make this something that was approximately the size of the window that we assume we're going to be on. Like I could make this 1200 by 630 and it would be the same size as the initial window size. But in this case, I've just chosen to make it very small, 1010. So there's 10 pixels in each of them, and then it will change whenever the window gets actually rendered. So these are all of our default values. So we've got a size of 1010, which we've also used for this empty image, basically. And we've also set the noise to either the default noise or whatever noise that we want. Remember, basic multi is 6 octaves of Perlin noise combined together. So it gives us a really nice image really nice data to deal with. We can, of course, set new noise. Say if we want to update the seed, which we do, then we set the noise and we call this redraw image. And this redraw image is where all of the real logic for how we turn Perlin noise into a beautiful image is located. Update size similarly changes the size of the image, sets the image to the new size, sets the size of the model to the size of the window, and then calls redraw. So the logic for these two is basically just, hey, if we want to change anything, then we have to redraw the image in these cases. In our redraw image function, this is the real interesting part here. So we're going to take the self.size, so the model.size.x and the model.size.y, and we're going to create 2 ranges for them from 0 to that size. So if it's a 1920 by 1080 screen, it'll be 0 to 1920 and 0 to 1080. And we do a Cartesian product on those. And what that gives us is basically every X with every Y. So we'll get 0, 0, 0, 1, 0, 2, 0, 3, and so on. So this will give us every pixel that we need to fill up that 1920 by 1080 area. The value here is just our noise function. So the Perlin noise has a get on it. We're using 2-dimensional Perlin noise, which is the X and the Y. We divide our noise by the noise step. So each of our X and Ys from our Cartesian product up here will be something like 0, 1, 0, 2, 0, 3. What we want those to be is 0 for the X, and then say 0.002 for the Y. And then the next Y is 0.004. This is because the Perlin noise algorithm, if we put in integers, will give us back 0 for all of those integers. That's just kind of the way Perlin noise works. So we want to make sure that we choose numbers that are between integers for most of our data. So in this case, if we had 500 steps, if we had a 500 by 500 window, we would have the number from 0 to 1 input into our noise algorithm. And then what we get back is a number from -1 to 1. And this is when we choose what kind of color we're going to output. The simpler case is grayscale. So if we are grayscale, we are going to map the range of the noise output, which starts from -1 to 1. So that's the value that we get back from the Perlin noise algorithm. And we're going to change that for something from 0 to 255. If you've ever worked with CSS or you know what a U8 is, this is that value, right? So if you set RGB and you set it to like 255, that's white. If you set it to 0, that's black. And we're just going to use the same value across all 3 RGB values. So we only need to do this once for this one mapped value. Now on our dynamic image, we can grab basically a buffer of pixels that we can then modify on a pixel by pixel basis. The buffer has a put pixel function, which allows us to take X and take Y which in this case, because we just talked about dividing it by the noise step, these are the actual pixel values. So it'll be 1, 2, 3, 4, 5, not 0.002, 0.004. And then we create an RGB value from those mapped values. In this case, because we're using the same mapped value in 3 different places, the RGB and NB, we get a grayscale image. We could also use luminosity here. That is an option in Nannou. I just decided to not do that when I was creating this. It's creative coding. You get to make choices like that. So that will give us the Perlin noise mapped across all of the other values. And again, to remind you what that looks like is this. So what we've got here is all of the pixels in that buffer mapped to one of the values that came out of the Perlin noise. And the Perlin noise goes from 0 to 255, which is why we've got some spots that look like they're leaning towards white, and then some spots that look like they're leaning towards black. A more interesting case is what happens if we decide that we want to do colors. And what I've chosen to do here is map the values that we're getting out of the noise function. So the noise is outside of this if statement. We get the same value, whether we're grayscale or not. We take that value, which is from -1 to 1, and we change it to be somewhere within the hue center range. So our default hue center is 0. Our default range is 180. So by default, this will be from -180 to 180, which is a full color circle. That includes every color from blue to yellow to green, etc. Then we create a new LCH color, which has lightness, chroma, and hue values. The lightness is a user-driven choice, although we could hook this up to the Perlin noise as well if we had, say, more dimensions maybe. And chroma is a lot like saturation. So you'll see as we move chroma up and down here, we create either a more saturated or a less saturated color. And then the hue is chosen based on that noise value. So because Perlin noise is a gradient noise, what will happen is that all of the values surrounding a particular pixel, say a green pixel, will also be kind of green, which is what gives us that really nice gradient look from our Perlin noise image. We take that LCH color and we create an RGB color from it. And then I map those RGBs to 255 from -1 to 1. And that gives us our output colors. So again, we've taken our values, RG and B here, and we have mapped them into a U8. And then we do the same thing. We get the mutable buffer, we put each pixel in its place, so X, Y, and then we map the RG and B here, and then we get a colored image. So at this point, what we've done is we've created this dynamic image, but we haven't rendered it anywhere yet. That's the responsibility of the view function that we haven't covered yet. Our view function runs on every frame, but in the case of this, we're basically generating one pane every once in a while, so there aren't really that many frames here. We set the background color, which we actually draw over with our image, so we'll never see this background. And then we take our dynamic image here, and this is the crucial part for Nannou. We create a texture, a GPU texture, from the image data that we generated. So we generated what is effectively like a PNG, and then we're saying, hey, take this PNG that we've created and turn it into a texture on the GPU, because we want to render this. So if we draw .texture and we pass in our texture, we will get the texture rendered to the screen. And of course, this is just some utility stuff that we explained in the last video. It shows the seed that we're using in the bottom right if we're using a custom seed. And that's pretty much it for the 2D Perlin noise. What we've done here is created an eGUI. That's pretty funky. I wonder why that's like that. Maybe I need to draw a background color in the eGUI window. But we have an eGUI like UI here for the debug UI. So we can change these values as much as we want. We can darken the lightness a little bit. We can change the chroma, which is again, the saturation that we were talking about. Let's get something really saturated here. And then we can change the hue center. So if we look at the grayscale, the dark spots are blue and the light spots are this orange, right? So if we change the hue center, we can reverse that, where now our noise has not changed, but only the place that we're mapping the colors onto has. So the blues are now in the light spot and the reds are now in the dark spot. And if we want, say, something a little bit less across the entire color spectrum, we can drag the hue range down a little bit. We can get just about any color combination we want. So let's go with something like that. That looks kind of cool. So I like these colors. And if we look at the grayscale noise, we can see the noise has still not changed. But if I change the seed by clicking on this, then the noise changes. The color mapping has not changed. So we're generating new noise, but we haven't changed the color mapping. So the same spots that are dark are still blue, same spots that are light are still pink. And if we change the seed again, we can do it again. Dark is blue, light is pink. We can just kind of click in here. This is jump, this is tidy, try to find something that we like. Let's try acid. I kind of like acid, so I'm gonna just save that out. Maybe I'll use that as the image for this video later. And that's it. I mean, we can play around with the hue ranges again. We can get more blues in here. See those oranges starting to peek through. We can reduce a little bit of the saturation if we want to. We can bring the lightness down, or we can go super light too, blow it all out. It's really creative coding. So you get this choice. We can go super saturated and get some nice hard lines around our blues, kind of start blowing a little bit of our colors out, or you can do whatever you want. And notice that the noise hasn't changed. Only how we're mapping colors onto that noise has changed. So I hope that you've enjoyed this visualization of 2D Perlin noise, and let me know if you try it. Leave a comment down below, ask a question. Happy to answer anything you've got, and I will catch you in the next video.